So the great idea now is, if you don't know any matroid theory, you're learning it, because if you take a thing over field and do this, you're doing what they do. Okay, so now here's the great answer. This stuff is really elementary. So over here we have this lattice LA. Okay? So here's one definition. A1 to AK, which is a subset of A, is independent. Over here, we're going to, okay, if and only if, well, I'll put parentheses here. If there's some rearrangement of these guys. So I think this definition is new for lattices. I mean, this stuff, or it was thought up 40 years ago. A1 prime to AK prime, a subset of generators. If you want to do general lattices, you can do this. B is the bottom. So if you have a lattice, you always L minus B. We never allow B in the generators because the empty set generates B by category theory. So you can either think LA or you think L, and the generators are everybody but B. B is the bottom. Okay, A1 to AK and A, or under this definition, is independent if and only if there exists a rearrangement. Okay, so A1 is less than A1 join A2 is less than, I'm sure, different than, okay, yeah, hey, okay, or, hey, you wrote it the same way. Okay, so so that's one, here, so here's the first, none of this is hard. We know what independence means here. We go, by taking the flats and the lattice, we get over to all these sets at intersection and these generators. And over on this side, A1 prime to AK prime, which on that side is just columns, is independent. There's some way I can rearrange them that you get this. Everybody understand? So, I mean, oh, you won't allow this, right? I like the line books. I like to say this was proved 47 years ago by somebody. Okay. So this is great. Okay, so this is what the definition, if you want new ideas, this is what the definition looks like over here in lattices. So the theorem is not very hard. A1 prime to AK prime here are independent if and only if, when you run through all this and go over here, this is true. Okay. The other one, now there's another great idea. Dilworth, yeah, Dilworth proved this 45 years ago. He should. I mean, this stuff is really, you can explain this to your roommate, right? Even if they're not math, right? Up to now? Okay. No, who's laughing? Okay. Pretty easy. Okay. Okay, here's another great idea. Here's another great idea. Okay. Okay, soon you have the lattice L, A, and okay, so at each point L of the lattice, you can look at, this is everybody less than or equal to L. Okay? Intersected with A. So write this, at each point of the lattice L, label it by that. So at each point of the lattice L, you look at everybody less than or equal to it. Go down and intersect with A. Okay? Now, take a chain from the top to the bottom of the lattice. And take a maximal chain. So that means you can't refine this. So T's at the top, then there's nobody between T and L1, there's nobody between L1 and L2, and so on. And you go to the bottom. Okay? So take a maximal chain. The longest one of those is called the height of the lattice if you count edges. Okay, and then you have a label. At every spot here, we'll call this the label of L. So at each point you have a label of T, and then you have the label So I have the label of T, and then I have the label of L1, and the label of Ln, and the label. Okay, and now take successive differences. So take this set minus this. So here, right, at this spot, when you have label Li, and you have label Li plus 1, here just take the set theoretic difference. Okay, so given any lattice in the world, you stand at L. Can we open the door? I'm getting warm. Oh, maybe it's this skirt. Yeah, are we allowed? Okay.
Yeah, we're allowed.
Okay. All right. I'm going to fade on you. Okay, so we have a chain from the top to the bottom, and we have a label, which is everybody below L intersect A, and then I take the set theoretic differences. Okay, and this will give me a partition of the lattice minus the bottom. So I take a chain, okay, so it's a natural thing. Now just take partial transversals. Meaning take a collection, a subset of, so if I give you a lattice, I can take a chain from the top to the bottom. They do this in geometry all the time, you know. Okay, a chain from the top to the bottom. You have the labels at each spot. Take successive, so we call those the partitions. Every maximal chain will give you a partition of the lattice minus spot. Okay, and now just pick some set of points that aren't related, meaning no two are in the same box. Okay?
Really, it's a partition, or how do you get a partition? Because maybe to change.
Here, this is the whole lattice. Okay?
Yeah.
Then you go to here, so you take the set theoretic difference.
Yeah.
So that's one box.
Yeah.
Then this box.
Yeah.
So in other words, two people are in the same box if they're between these two.
Yeah.
That's the partition.
You mean that? Okay. I didn't know.
Yeah, sorry. Okay, now you're happy? Yeah. Okay, so this is a partition or equivalence relation of the lattice minus B. And now look at a set of points that aren't equivalent, meaning everybody's in a different box, okay?
Yeah, okay.
Okay, so that's the theorem. The theorem is if you start with the Boolean matrix and you go over to the lattice of flats, okay? Then over there, if you take this definition or you take that definition, that's how you get the original definition. Everybody, you understand? Great. Okay. All right. Okay, flip this for a while. Keep going. We're not going to do graphs. You've got to go fast. Till you keep going. There, good. Next one. Okay, I think I've already told you that. Do the next one. Yeah, none of this is very important. Wait, back up one. Leave it there. Okay, let me tell you one thing. If I have a lattice over here, how do I get a matrix that it comes from? So we now see, and the answer is, you do the following. The matrix of this lattice is it's going to be an L by A matrix. Okay, but now here's the tricky thing. The entry here, MLA, it's going to be 0 if A is less than L and 1 otherwise. Now see, this is a little weird. See, it seems backwards. That's why we call this C independence. Remember, I took where the rows were 0. So, writing down this matrix. So in other words, if I stand LA, you would think I'm going to write a 1 if A is less or equal to L, but I write a 0. Okay? So write down what everybody thinks you're going to write down. Of course, you have a left, right, and then change 0 to 1 and 1 to 0. So if you write down this matrix, then everything works. So if you start M and you go over to LA, and where this is the flats of M and the closure of B, okay, then when you come back and you get the matrix of LA, these are going to give the same represent. And how are these related? Now you've just taken all the rows here and done the Boolean join, where 0 join 1 is 1, 1 join, the Boolean join, the real one. Okay? So in other words, if you start with the matrix here, go over to this and go back to this, all you're doing is if the original matrix was like 1, 0, 0, 1, and you went over and back, then you're going to put in, well, 0, 0 is a, you put in that one, and then you put in the join. Intersection is going to, see, we went to zeros. So joining the rows in the usual Boolean sense, right, is intersecting.
What's an example of a simplicial complex that is not Boolean representable?
I'm sorry, it's what?
What's an example of a simplicial complex that is not Boolean
Yeah, okay,
representable?
the smallest one is yeah, on 4. It's, if you're on 4, let's see, the way we do it, so we do all subsets, all less than or equal to 2 subsets. And we exclude that to, oh yeah, exclude, okay, and add 1. That one won't work. Because all the Boolean ones satisfy this. There's a 171-page paper now. You actually know a lot. I haven't even got to any of that. Okay. And the reason is all the Boolean ones satisfy point replacement. So if P is independent, so that just means the column above P isn't 0, which if P is independent and I is independent, then there exists a Q in I. So I minus Q plus P is independent. This is another non-controversial axiom. It's much weaker than my matroid axiom. If P is independent, meaning, okay, and if I is independent, then you can put P, you can throw away a Q and put in a P and keep it independent. They all satisfy this and that doesn't. Okay? Now, if you have PI, Boolean representability does not go under a contraction. So if you're a simplicial complex such that your subs and your contractions are all PI, then you're a matrix. Okay. So this is a wider collection. How much time do I have?
5 minutes.
What do I want to do? What do I want to do? Okay, okay. So now you can develop quite a big theory. What do I want to say? I guess it follows matroid. Oh, the big theorem is what do I mean? Is that all matroids? This is a new theorem. It's not very hard. All matroids have Boolean representations. And the proof is, take M of the geometric lattice. So if you know, okay? Now, matroids don't all have a matrix representation, so then we get into the rotor conjecture, which I don't think is so important. At any rate, but now we have a representation, so let me talk about it. If you have VE that's Boolean representable, okay, then you can look at all the Boolean representations, okay? And even if it's a matroid, so you just restrict a matroid. So if you look at the set of all, representations, so we're going to look at all the matrices that represent this simplicial complex. Okay, fine, and we're going to call the matrices we're going to call them the same if when you Boolean join the rows, they're equal. So, okay. But still there's a lot of them, even if we're going to do the Fano plane. So if you look at all the Boolean representations of a matroid, or more generally a Boolean representable simplicial complex, that forms the lattice itself, where the strong or weak maps are sup maps. Once you know things are really L1A and L2A, then if there's an arrow this way that's identity on A, then you want to say this is less than this. So the strong or weak maps are going to be sup maps here that are identity on A. So there's none or one. So you're going to get it. So now, even in the classical case, Fano plane or anything, you have a lot of Boolean representation where the geometric lattice is giving the biggest one. But there's a lot smaller. Okay? Okay, also, there's a join in there, stacking. If I have two Boolean representations, M1 and M2, I can stack them. So that's the join. So we actually have a representation theory for every matroid, or more generally for every simplicial complex Boolean. This has not been utilized. We haven't even calculated what it is in the classical cases.
And for matroid theory, people use representations to stratify the Grassmannian. For example, they relate to algebraic geometry.
What?
In the classical theory of matroids, people use the representations of a matroid to stratify the Grassmannian. Do you get some kind of natural stratification here of some object? Or?
Well, this is better because every matroid has it. Every matroid's got it.
Yes.
Right? And we have a representation theory, meaning everybody's a direct sum of the. Okay. Yeah, this is not what. Okay. We only thought this up 6 months ago. So, I mean, the homework problem is go get Oxley's book and find. Okay, the other thing is you want to find the minimal representations, okay, under this order. You want to find the SJIs, the strict join irreducible ones. Everybody is a direct, somebody is strict join irreducible if you can't write it this way except using itself. So everybody, you want to find all the minimums, you want to find all the SJIs. The SJIs, everybody can be written as a stack, so you actually have a representation theory. Okay, and I'm sure the representations that you're talking about and will all fit into this. The point here is every guy's got one of these. Okay, and we have some structure. And then the other thing that will come in is min degree. What's the smallest matrix? Like the Fano plane is 4. Given the Fano plane, the minimal representation matrix, you got to take 4 lines that miss a point. And then write down the matrix. So in the Fano plane, and I'll stop in a minute. In the Fano plane, take 4 lines that miss a point, and then write out the matrix. In other words, make this line 1, 2, 3, 4, 5, 6, 7. So now you write a matrix that's 0, 1, 2, 3, 1 every place else, so on, so on, so on. If you write down that matrix, which will be 4 by 7, that's minimum. So the first thing is now we know how to, even doing the uniform. No, so nobody, well, okay, I guess the final thing I say is you could go to the simplicial complex and want to compute the homology. Okay, well, they're shellable. Under mild, just like we know every matroid.
You mean if it is Boolean representative, is shellable? Is that what you're saying?
If you take, yes. Under sorry. Dimension 3, so we can prove. Probably true in general. Dimension 3, we proved it, and you need some mild connectivity conditions. But yeah, probably in general it's true. Shellable means you can actually calculate the homology. That's the only time I know how to. Shellable will imply it's a wedge of spheres up to homotopy. I think that's enough, right? Okay. I mean, there's 100. Okay, I think already, and if you look under Rhodes or Silva in the archive, I think there's 50 pages in it, but there'll soon be 180. Okay.